Hello everyone. Let us see now some of more examples on application of Laplace transform. There is a 91th example of our second chapter. Question is like this: solve the following equation. These are the differential equation by the Laplace transform method. The equation is d square plus n square. D means derivative. We have to convert first this equation into dash form. Okay, then only we can apply our regular formulas. D square plus n square into x is equal to a into sine nt plus alpha. N is also constant, alpha is also constant. Here our variables are only x or y and t. Here initial conditions are given on x, that is x is equal to dx. Dx means derivative of x, that is x dash. Both are 0 at particular point t is equal to 0, that means these are the initial conditions. Okay, let us see some let us rewrite this equation in our regular usual notation. First of all, we can replace x by y so that we can write the all formulas in our regular manner. First replace, this is a dummy variable, x is equal to y in above equation, and conditions are here y is equal to 0 when t is equal to 0 means y of 0 is equal to 0 from here, and d of y, x is replaced by y, and d of y means derivative of y at particular point 0, that is y dash of 0 is 0. Okay, now we have this equation, take x inside, that is d square x plus n square x is equal to a into sin nt. This is as it is. Now we replace here x by y, that's why this becomes in dash form as y double dash plus n square y is equal to a into sin nt plus alpha. Okay, now next step will be taking the Laplace on both sides, that is L of y double dash plus n square L of y is equal to a into Laplace of sine. Okay, we have Laplace of sine at only. This is given in the form of addition of angle, that's why we have to use here sine a plus b formula. Okay, and here a regular L of y double dash formula is this: minus y dash 0 minus s into L y of 0 plus s square L of y. This is L of y double dash plus n square as it is, L of y as it is, a into this is sine nt plus alpha as it is. Now we have to just take this separately, Laplace sine of nt plus alpha. First call this as equation number 1. Now consider this Laplace of sine. Just use the formula of sine a plus b is sine a cos b plus cos a sine b. Okay, split this formula as it is. Now what is our variable? Laplace we are taking of t function. That's why apart from t, whatever is comes, that is constant. Here alpha is a constant, that's why sine alpha and here cos alpha, these are constants. Okay, take outside of the Laplace, we take cos alpha into Laplace of sine nt plus sine alpha into Laplace of cos nt, because these are constants, because they these expressions or these functions doesn't contain t. Okay, that's why now Laplace of sine t is n upon s square plus n square, and Laplace of cos is s upon s square plus n square. Rest of the terms as it is. Now final answer is n into cos alpha plus denominator is same, combine that s into sine alpha upon s square plus n square. This is the Laplace transform of this RHS side we have just calculated. Okay, now put this value in this equation we get, and this ultimately and the same equation put this value y dash of 0 is 0 and y of 0 is 0. Here in this equation we get this 0 0 plus s square L of y plus n square L of y is equal to a into this a, don't forget the constants in the examples, a into this term. Okay, now from these two, L of y gets common, and s square plus n square as it is equal to a into this as it is. Okay, remove the brackets. Now again s square plus n square take on this side, we get s square plus n square bracket square. L of y is equal to a into this numerator as it is, and this becomes square. Okay, now take a outside, or you can take in a inside also, and L inverse of, take L on that side, we get L inverse of n into a cos alpha upon this plus a into s sin alpha upon this, and we have to find out inverse of this function. Okay, now this is the Therefore y is equal to a n, these are constants. Only t, or in the inverse function only s is our variable. That's why a and n and alpha are the constants. L inverse of this plus a into sine alpha is a constant. Take outside L inverse of s upon this bracket square. Okay, call this equation number 2. Now we have to find out this two inverses. Okay, that's why consider first inverse this. Let L inverse of 1 upon a square plus n square bracket square. We have to consider this first. Now if this in such a type of examples we can use any method to find out inverse Laplace transform. Okay, now throughout the inverse Laplace transform, convolution theorem is the only easiest way to find out inverse Laplace transform of complicated terms. Okay, so don't use the partial fraction here. Whenever there is a question where method is not involved, they just ask for finding out the inverse Laplace transform, and you have the choices for partial fraction and convolution theorem. Use convolution theorem only. Okay, convolution theorem is the most easiest way than partial fraction, because partial fraction is a lengthiest examples or lengthiest way. Now here in the both inverse we are going to use convolution theorem only. That's why for this, convert this function into 2, that is one bracket 1 upon s square plus n square, and other bracket, this square is there, that's why other bracket 1 upon s square plus n square. Now find out the inverse of both. What is the inverse of both? This is the homework to you. Okay, you have to find out the inverse. This is the homework. Use convolution theorem. Okay, this is the homework for you. Phi 1 inverse, calculate phi 1 inverse, then phi 2 inverse, call them as f1. This is sine, this is also sine, and use the integration formula and calculate the answer. Okay, after that consider this second, this one. This is also we are going to use by solve it by convolution theorem. For that, split it into two. This example is same except this numerator only s is there. That's why one s can be given to the one bracket, that is phi 1. Consider phi 1 is equal to 1 upon s square plus 1 bracket n square, and phi 2 is equal to s upon 1 bracket s square plus n square. This is cos and this is sine. Okay, again use convolution theorem to solve this example and calculate the answer. Okay, that's why from 2 the answer is this. Okay, calculate the both the answers and put in this equation to find out value of y. And again you have to resubstitute x, because our original question is in terms of here. Our original equation contains x. This is our replacement. That's why at the end of the example just replace or resubstitute y is equal to x. This is our answer. Okay, these are the homeworks for you. Now again some homeworks for you. Use partial fraction method to find out inverse Laplace transform of the following. Use partial fraction here. Okay, in this first 92 example, take common, you can take common s and s plus 2. Okay, both are linear factors, a upon s, b upon s plus 2, in that way. Okay, these are the homework. And this is again take the s common, we get s square plus 3s plus 2. Again factorize this. This is s plus 2 and s plus 1. These are 3 brackets, linear brackets. Okay, here is the hint, that is take s common. Next example, find, this is also homework for you, L inverse of s plus 3 upon s plus 6s plus 13 bracket square. Okay, what you have to do, take for first this is, it must be square. Okay, this is also homework. And okay, this is also for this example is for convolution theorem. Not, these are only 2 examples for partial fractions. This one homework for convolution theorem. Okay, first what you have to do here, just adjust the square here first. Okay, this is s plus 3 bracket square, you can adjust here, and this whole bracket square is there. Okay, that's why by using shifting property or exponential property, first convert this into simpler one and then use the convolution theorem for the rest of the factors. Okay, now here next homework is L inverse of 64 upon 81 s raised to 4 minus 256. If you see this, these are the perfect squares. Take 64 common, these are the hints. 64 common, L inverse of 1 upon, this is a square minus b square formula. 256 is a 16 square and 81 s raised to 4 is a 9s square square. Okay, that's why use a square minus b square formula. Here we get a plus b into a minus b. Again this can't be factorized because of plus sign, but this can be factorized into again 3s. This is 3s square, this is 4 square. Again a square minus b square formula we can apply here, that is 3s plus 4, 3s minus 4. Okay, this we can't convert into formula because a square plus b square is not there in the mathematics. Okay, that's why this is quadratic formula, this is linear, and this is also linear. Okay, how can we write this? That is, for this quadratic factor as plus b upon this, these are the linear factors c upon this plus d upon this. Okay, this is the homework for you. ABCD values are this, and resubstitute here you get and split this formula. And after to calculate L inverse, just take 9 common from this, and this also 3 common from this, and here also 3 common from this, because in every inverse Laplace transform formula, coefficient of s or coefficient of s square in the every formula is 1. Okay, this is the end of the chapter. This is your next make this 11th assignment. Okay, till this chapter. Now we are going to start our next chapter, that is our next assignment number 3 and sections. Okay, our next chapter is Fourier transform, like Laplace transform and inverse Laplace transform. See, in M3 there are total 6 chapters. Out of 6 chapters, these two what we have just completed are the biggest chapters. Okay, that's why we are getting the more time for that. Laplace and inverse Laplace. Rest of the 4 chapters are very easy and very less in the length. Now first we are going to consider this in Laplace transform. You have seen that an inverse Laplace transform also there are almost 100 questions we are covering. Okay, we covered already, but in after these 2 chapters, hardly in this chapter there are 30 to 40 examples only. Okay, now let us see our next chapter, that is Fourier transform. Let us see first definition. The integral transform. Let us start with the sum of the definitions. The integral transform before Fourier transform. See, in this chapter there are total 2 parts. First part consisting of some examples of Fourier integral. Okay, and next point will be Fourier transform. Okay, these are the basically 2 points, main points of the Fourier transform chapter. Now let us see some definitions. The integral transform of a function fx is denoted as I of fx, and it is defined as I of fx, that is integral transform of fx, is equal to integration x1 to x2 f of x, this function f of x, into k s of x dx, where k sx is called kernel of fx. This function's kernel of fx. This is called kernel of fx. And if you go on putting the values of kernel, we can get different transforms. Okay, like suppose if k of sx here in this chapter, if k of fx we have put e raised to I sx. What is I? I is the imaginary number. You know that I square value is -1, or I is the root of -1 value. This is a basic complex number. e raised to isx. We have the Fourier transform of fx is given by this formula. Capital F of s is equal to integration minus infinity to plus infinity fx, this function fx e raised to isx dx. Remember that whatever the function here which is attached to exponential, we have to take that variable here. Okay, with respect to which variable is very important throughout the chapter. Okay, here x, here also should be x. Okay, this is the basic formula for Fourier transform of function fx. This can be again equal to f of fx. Okay, f of fx is shortly written as f of s because it is ultimately function of s, and it is the integration. Like for example, Laplace of function, we can write it as L of ft, or sometimes we call it as phi of s. Okay, in the both the way. Also, Fourier transform also can be written in the form of f of fx, that is Fourier transform of fx, or f of capital F of s. Okay, now let us see the Fourier integral definition and some notes. If fx is a periodic function in the range of minus infinity to plus infinity, what is our range? It must be a real line, a real number line, that is minus infinity to plus infinity is our domain. Then the Fourier integral, Fourier transform is different and Fourier integral is different. Okay, Fourier integral of a function is defined as, these are the very important formulae. Fx is equal to 1 upon pi integration 0 to infinity into double integration again minus infinity to plus infinity fx cos lambda t minus x brackets complete dx dt. Okay, this is the basic definition of Fourier integral. But in while solving the examples, we are going to consider the simplest form of this formula. These are the three formulae you have to mug up instead of one formula because it consists of double integration. But we are going to use these three formulas to the simplest formulas to solve the examples. Okay, now above formula can be rewritten in the form of fx is equal to integration, single integration 0 to infinity a lambda cos lambda x plus b lambda sin lambda x bracket complete d lambda. Okay, now where a lambda is equal to 1 upon pi is there, minus infinity to plus infinity, integration limits are different, fx into cos lambda x, where a lambda in the you can mug up as in the integration of a lambda cos is there, in the integration of b lambda sin is there. Okay, fx cos lambda x, now here x is there, d lambda. Okay, again 1 upon what is b lambda, just replace cos by sin here, that's it. Just mug up these two, you can b lambda, ultimately you can change make the change in a lambda, like replace cos lambda x by sin lambda x here. Okay, now these are the some three formulas, basic formulas of Fourier integral. Okay, now let us see some examples depend on the Fourier integral. Before that, let us see some notes here. Mod of x less than or equal to a, the meaning of this is x is lies between minus a to plus a, and mod of x greater than a means x otherwise. Apart from these values, for example, suppose how it comes, let us see. Mod of x is less than or equal to a. Okay, what is the mod x value? It is x when x greater than 0, it is minus x when x less than 0. This is a basic definition of mod x. Okay, mod x is either is it is negative or positive. That means mod x is, if it mod x is less than or equal to a, and minus x also less than or equal to a, right? Both the values are included here and less than or equal to a. Now to convert this into one form, just multiply both the side of this inequality by minus sign. See, in inequality, if suppose x is equal to y, if multiply both the side minus sign, this sign doesn't change. equal to sign doesn't change. Okay, but while inequalities where suppose x is less than y, and if you want to multiply both the side by minus sign, okay, then this sign get reverse, like x minus x is greater than minus y. How it come? Let us see some small example. That is 1 is less than 2. Okay, right? Then multiply both the side by minus 1 minus sign. What we get? Minus 1 must be, this is less than, reverse to greater than minus 2. Obviously minus 1 is greater than minus 2. Understand? That's why mod of x is x less than or equal to a. Multiply this by minus 1. Both the side we get x less than turns to greater than a, greater than or equal to. Now combine these two. What we get? X is, this is less than or equal to x, and x is greater than or equal to minus a here. Sorry, minus. Okay, minus minus gives plus, here minus a. Minus a. Right? Therefore, mod x is less than or equal to a means x lies between minus a to plus a. But our integration limits are minus infinity to plus infinity. That's why apart from this minus a to plus a, we are taking all the values 0. Okay. Okay. Now let us consider first example. Find Fourier integral representation. That means Fourier integral of the function, rectangular function is given by f of x is equal to h of bracket 1 minus mod x bracket complete, where h is a heaviside unit step function. Okay, we already studied in earlier Laplace or somewhere unit step functions Laplace. Okay, where heaviside unit step functions values lies between 0 or 1. Okay, that is the h value or h function notation. Now we have to find out, what is the question? We have to find out Fourier integral of or Fourier integral representation of the function, this function. Okay, now we know the Fourier integral. Now Fourier integral representation of fx is given by this formula. Okay, this already we know, by this is the definition. You have to mug up this formula. Fx is equal to integration 0 to infinity a lambda cos lambda x plus b lambda sin lambda x. Okay, where a lambda and b lambda we have to find out. What is a lambda? 1 upon pi integration minus infinity to plus infinity fx cos lambda x dx. Okay, now we have to put value of fx here. Okay, what is our function? Heaviside's unit step function. Okay, for that this is equal to 1 upon pi h of 1 minus mod x. Now heaviside unit step function lies between minus 1 to plus 1. This is a graph of this function. Okay, what is this graph? Heaviside's unit step function 1 minus mod x. Why we draw this? Because we want to know the limits of this. What is our limit of integration? Minus infinity to plus infinity. Here infinity is there, it is here minus infinity is there, but this heaviside lies between minus 1 to plus 1 only. Okay, that's why rest of the terms, rest of the integration in this interval 1 to infinity and minus 1 to infinity, the function value is 0. Okay, that's why this integration limits minus infinity to infinity change to minus 1 to 1. Okay, and value of heaviside function is 1. Okay, cos lambda x dx as it is. Now 1 into cos lambda is cos lambda, integration is cos of integration of cos is sin lambda x upon lambda x derivative divide with respect to x, that is lambda. Take lambda common, we get 1 upon out of the bracket, we get 1 upon pi lambda. Put the upper limit 1 in x, we get sin lambda minus lower limit sin of minus lambda. We know sin of minus theta is minus sin theta. That's why this minus gets plus, and next sin lambda plus sin lambda becomes 2 sin lambda upon this as it is pi lambda. Okay, now again b lambda. What is the difference between a lambda and b lambda? Here in this, instead of cos we get sin only. Okay, and the same way we have to solve this integration. This integration value becomes 0. You can check out this integration. Now we have to put this a lambda and b lambda value here. What we get, therefore Fourier's integral x representation of function fx is given by fx is equal to integration 0 to infinity is there a lambda, that is this cos lambda x, plus b lambda is 0, that's why just write 0 d lambda. That's why take 2 upon pi constant outside, because see this integration is with respect to lambda, that's why lambda is not constant here, x is a constant with respect to this integration. But we cannot take x outside of this integration from cos, okay, because this is in angle. Now take 2 upon pi is the only constant, take outside. Answer for this is 0 to infinity sin lambda cos lambda x upon lambda d lambda. We don't need to solve this integration because we want the Fourier integral only. The answer must be the integral only, integration only. We don't need to solve this integration. Okay. Let us see the next example. Express the function. This is function given fx is equal to, it is in interval form. It is 1 for mod x less than or equal to 1, and it is 0 for mod x greater than 1 as Fourier integral. We have to find out Fourier integral of this function. This question means this, that we have to find the Fourier integral formula for the function given by this, and hence evaluate. We have to find out this answer using the Fourier integral of this function. Let us start to find out first Fourier integral of function. Let us write down first function fx is equal to, it is 1 mod x less than equal to 1 means it is like x lies between minus 1 to 1. Okay, and mod x greater than 1 means otherwise it is 0. Okay, that means in the number line this is 0, this is minus infinity, this is plus infinity. Okay, and this is 0, this is minus 1, this is 1. Minus 1 to 1, the function value is 1, and rest of the values is 0. Okay, these are 0 values. Now Fourier integral is given by fx. This is a formula as it is, integration 0 to infinity a lambda cos lambda x plus b lambda sin lambda x bracket complete d lambda. Call that equation number 1. We have to find out a lambda and b lambda only, where a lambda is 1 upon pi integration minus infinity to plus infinity fx cos lambda x dx. We have to find out, we have to put this function fx value here. What is fx value? 1 in between minus 1 to 1. Rest of the interval value of fx is 0. That's why we don't need to write this, split this integration into 3 integrations. That is first from minus 1 to 0, then minus 1 to 1, and 1 to infinity. But both the values of this minus 1 to minus infinity and 1 to infinity are 0. That's why we don't need to write the those integration whose values is 0. Only middle integration or middle interval is exist only. That's why minus 1 to 1 fx value is 1 cos lambda x dx. Okay, earlier solve this integration, we get answer 2 sin lambda upon pi lambda. This is the same integration as earlier example. This is the answer for a lambda, and for b lambda just replace cos by sin here. Rest of the terms as it is. Answer for this is 0. Okay, just check out this. There is 1 sin lambda is minus cos lambda x, and after putting values we get, we have here cos of minus theta. We know cos of minus theta is plus cos theta. That's why cos lambda x gets cancelled and answer becomes 0. Okay, now put this value in this integration, we get Fourier integral formula for this fx is given by fx is equal to integration 0 to infinity a lambda, that is this value as it is, into cos lambda x d lambda. Okay, this is the value for, and take 2 upon pi constant outside, we get 2 upon pi fx is equal to 2 upon pi integration 0 to infinity sin lambda cos lambda x upon lambda d lambda. Okay, now what we have to do, this is the first answer. We are just found just in Fourier integral for this function. Now hence evaluate questions are depend on the earlier answer. What is our answer? This. What we have to find? This. Okay, now if you observe this example and this example integration, what we don't need here, We need here only sine and upon t. T is a dummy variable, okay? Here lambda is a variable, nothing difference. Sine t upon t only we want. Here sine lambda upon lambda only we want. We don't need cos lambda x. That's why where the integration is with respect to lambda, we lambda values vary from 0 to infinity. We cannot put value of lambda where lambda is a variable with respect to integration with respect to lambda. That's why we have to put values of the variable which is present apart from lambda. What is that variable? X. That's why by putting values of x, because fx we have this and we know x values and we know functions value here already, okay? That's why we don't know lambda value. What is the lambda value? 0 to infinity we cannot put here because x is the integration is with respect to lambda. That's why put here for what value of x this cos lambda becomes 1. We know cos 0 is 1. That's why put x is equal to 0 in this integration. What we get? F of 0 on both sides, obviously f of 0 is equal to 2 upon pi integration 0 to infinity sin lambda upon lambda as it is, cos 0 is 1, d lambda as it is. Now we want this integration, take this pi by 2 on that side, we get pi by 2 f of 0. How to calculate f of 0? By putting x is equal to 0 in function. What is our function? This is our function or this is our function. Where we 0 lies in this function, in -1 to 1 0 is there. That's why we can put x is equal to 0 in first value, but here only constant number is there. That's why for x is equal to 0 function value is 1. Put that value here, we get pi by 2 into 1. Answer is pi by 2. That is what we want to prove. Okay. Okay, now let us see some next formulae. We have just seen Fourier integral. Now we are going to see Fourier sine and cosine integral. Sine cosine means sine and cos. Okay, now first formulas, these are 4 formula total. Fourier cosine integral of this function, let f of x be the any function, then Fourier cosine transform, Fourier cosine integral is given by Fourier. You can call it as Fourier cosine integral or just cosine integral. Okay, there are only two difference, integral and transform. These are two only main difference. Otherwise everywhere Fourier is there. Then cosine integral is given by f of x is equal to integration 0 to infinity a lambda cos lambda x d lambda, where a lambda is 2 upon pi integration 0 to infinity fx cos lambda x dx. Okay, this is the formula for Fourier cosine integral. Here Fourier sine integral. What is the difference between cosine integral, sine integral? Just replace everywhere by cos by sine, a lambda by b lambda. Okay, therefore this is called Fourier sine integral. F of x is equal to integration 0 to infinity b lambda sine lambda x d lambda, where b lambda is equal to 2 upon pi. Here again 2 upon pi, same formulas are there. Just you mug up one formula, you can prepare the second formula as it is. 0 to infinity fx sine lambda x dx. Okay, remember this, here b lambda, that's why lambda is here. Here x is there, that's why x is there. Okay, don't make confusion, because total chapter, in the whole chapter, the integrations are there, and integration with respect to which variable is very important. Okay, now let us see the next example. Depend on this Fourier integral. Okay, using the Fourier integral, question is like this: Fourier integral representation show that this we have to prove. Okay, if you observe first integration, what is it integration? We have to show that this integration is equal to this. If you observe this two, this integration is 0 to infinity omega sin x omega 1 upon omega square d omega, and this is here a cos omega x there, and here also what is the, here see, in the cosine integral formula a lambda cos lambda x there, in the sine integral formula b lambda sin lambda x there. That's why in this integration we are going to use Fourier sine integral formula. Okay, let us write down first the Fourier sine integral formula. Okay, here the Fourier sine integral number 1 we are going to see in the number 1 first is given by fx is equal to integration 0 to infinity b lambda sin lambda dx d lambda. Call the equation number 1. If you observe these two, okay, sin lambda x, this integration is here, and r this is equal to LHS side is fx. That's why what is our function here? This is our function. Okay, that's why let us start first, where b lambda is equal to 2 upon pi integration 0 to infinity fx sin lambda x dx. Now we want to put the value of function here. What is the function? RHS side of this equation, pi by 2 e raised to minus x, where x is obviously greater than 0, sin lambda x dx. Now take pi by 2 outside and cancel with this 2 by pi. We get integration 0 to infinity e raised to minus x sin lambda x dx. Okay, now we are going to use a formula here. What is our formula for this? You can write note as first integration e raised to ax sin bx dx. What is that? E raised to ax upon a square plus b square into bracket a sin bx minus b cos bx. Okay, and second integration e raised to ax cos bx dx is e raised to ax upon a square plus b square. These two terms are same. Start with a cos bx, for cos plus sign is there, b sin bx. Okay, these are the formulae we already know. We are going to use this formula here. Okay, if you observe these two formulae, what is a here? Here in the exam you are going to you have to write this. Here also you write this integration formula. Here a is equal to minus 1, and what is b? Lambda. B is a coefficient of angle of x. Here x coefficient is lambda. Okay, now use this formula here. What we get? E raised to minus x upon minus 1 square, that is 1, plus b square is lambda square into bracket a sin lambda x minus b, that is lambda cos lambda x. Integration 0 to infinity. Now put the value here. We know already what is e raised to minus infinity value, 0. Remember that. Okay, and anything raised to 0 is 1. You know that. Now here put upper limit first. E raised to minus infinity is 0. Total terms become 0 for upper limit. That's why 0 here. Now minus lower limit, you have to put 0 in x. E raised to minus 0 is 1 upon 1 plus lambda square into bracket as it is. Sin 0 is 0. Cos 0 is 1. That's why answer for bracket is minus lambda. Now minus minus gets plus. Answer is lambda upon 1 plus lambda square. Okay, now put this value b lambda here in this formula sine of the Fourier sine integral. We get from equation number 1 fx, that is our formula pi by 2 e raised to function e raised to minus x is equal to integration 0 to infinity b lambda, that is lambda upon 1 plus lambda square into sin lambda x d lambda. Okay, now we want this integration, take on this side, we get pi by 2 into e raised to minus x. Now this is we want to prove here. What is the instead of omega, here lambda is there, it is a just dummy variable, that's why just put lambda is equal to omega or w everywhere, dummy variable. We get integration 0 to infinity w or omega sine omega x upon 1 plus omega square d omega is equal to pi by 2 here e raised to minus x. This is our first answer. Okay.